Welcome to today's paper reading. Today's paper is titled, Diffuse to Choose, Enriching Image Conditioned in Painting and Latent Diffusion Models for Virtual Trial. This paper was published on the AR-14 preprint by Mehmet Saygin Seyfioglu and colleagues from the University of Washington and Amazon. The abstract highlights the importance of virtual trial and online shopping, where buyers can visualize products in their settings. Diffusion models, while suitable for Inpainting, often lack the ability to capture fine-grained details. DreamPaint models, on the other hand, preserve details but are not optimized for real-time applications. The paper introduces Diffuse to Choose, a novel model that efficiently balances fast inference with high-fidelity detail retention and accurate semantic manipulations. This approach incorporates fine-grained features from reference images into the diffusion model's latent feature maps, using a perceptual loss to further preserve details. Extensive testing shows that Diffuse to Choose outperforms existing zero-shot and few-shot diffusion in painting methods. Figure 1 illustrates the capabilities of Diffuse to Choose, DTC, a system that allows users to virtually place any e-commerce item in any setting. The key feature of DTC is its ability to ensure detailed and semantically coherent blending of the item with the background, including realistic lighting and shadows. This technology enhances the online shopping experience by providing a more immersive and accurate visualization of products in various environments. The Vidal model is designed to enhance online shopping by providing an immersive experience where users can virtually try products in their personal environments. This model functions as an advanced semantic image composition tool, capable of handling any in-the-wild user image and integrating products seamlessly. Existing solutions, however, are often specialized and limited in scope, such as GN-based models for specific clothing segments or expensive 3D AR/VR technologies for furniture. Diffusion models represent a significant advancement, offering a more comprehensive approach with geometry and physics awareness, as demonstrated in recent studies. These models can be fine-tuned with few-shot learning, making them adaptable but still not fully meeting the real-time requirements for a Vidal model. In the realm of virtual try-on, existing models typically employ warp and paste techniques, utilizing additional inputs such as pose and human parse maps. Examples include Vuitton, which uses a two-step synthesis and refinement process, and Vuitton HD, which aims for higher resolution images. Try-on GN, on the other hand, relies on a purely latent model but often lacks fine-grained details. For diffusion-based image editing, creating realistic composites involves superimposing objects from one image onto another. The paint by example (PB) method, however, has limitations due to its reliance on the CLS token for image conditioning, leading to significant detail loss. To address this, the Diffuse to Choose (DTC) method was introduced, leveraging an auxiliary unit to preserve reference image details. In the context of diffusion in painting models, the process involves a Markovian approach where noise is gradually introduced and then subtracted to transform the image, conditioned by the reference image's embeddings. Figure 2 illustrates the pipeline of Diffuse to Choose, DTC, a novel diffusion-based image conditioned in painting model. The process begins with masking the source image and inserting the reference image within the masked area. This pixel-level hint is then adapted by a shallow convolutional network, CNN, to align with the variational autoencoder, VAE, output dimensions of the source image. Subsequently, a UNet encoder processes the adapted hint. At each UNet scale, a feature-wise linear modulation, film, module finally aligns the skip-connected features from the main UNet encoder and pixel-level features from the hint UNet encoder. Finally, these aligned feature maps, in conjunction with the main image conditioning, facilitate the inpainting of the masked region. Red indicates trainable modules and blue indicates frozen modules. Figure 3 illustrates the pipeline of paint by example, 40, specifically adapted for the Vidal case. The diagram highlights the architecture where red modules are trainable, blue modules are frozen, and orange pathways represent skip connections between the encoder and the decoder. This setup leverages clip embeddings of the reference image for conditioning the diffusion model, aiming to preserve fine-grained details and ensure seamless integration of the product image within the mask-defined region of the source image. The method vidal is formulated as an image-conditioned in-painting task. This involves integrating a single product image into a user-specified region within another image, ensuring the preservation of the product's fine-grained details. To enhance this process, the authors explored different methods of integrating a hint signal into the main unit. These methods include direct addition, feature-wise linear modulation, film, and cross-attention. Among these, film is found to be the most effective, as it specifically enhances the feature channels essential for preserving fine-grained details. Additionally, various hinting strategies are tested, such as using canny edges or holistically nested edge detection (HED) features. However, directly using the reference image is found to be the most effective, as it conveys the entire spectrum of details from the reference image, rather than focusing solely on high-frequency details. Figure 4 illustrates the process of integrating the hint signal into the auxiliary unit. First, the hint signal is stitched into a blank image within the masked region. This combined image is then summed up with the latent masked input. Finally, the resulting representation is fed into the auxiliary unit for further processing. Figure 5 illustrates the capability of Diffuse to Choose (DTC) in handling a wide variety of e-commerce products. It showcases the model's ability to generate images using in-the-wild images and references, demonstrating its versatility and practical application in real-world scenarios. This figure highlights DTC's effectiveness in preserving the fine-grained details of products while ensuring their seamless integration into the scene, fulfilling the criteria for the vidal use case. In this section, we discussed the experimental setup and the various ablations performed to optimize our models. Firstly, we detailed the dataset and implementation specifics. We compiled an in-house dataset of 1.2 million samples and also utilized the Vitan No-Face public dataset. Our model backbone is Stable Diffusion version 1.5. Moving on to the Paint by Example (PB) ablations, we made several modifications to the original PB architecture, including the use of DynOv2 and integrating perceptual loss. These changes are illustrated in Figure 6. Lastly, for the Diffuse to Choose (DTC) ablations, we explored different hint pathway strategies and integration techniques, such as direct addition, film, and cross-attention, to improve the model's performance. Figure 6 illustrates the effect of integrating perceptual loss into the image generation process. By using an ImageNet pre-trained VGGNet, the perceptual loss helps in aligning basic features such as color and certain textures between the generated and the source images. This integration enhances the quality of the generated images by ensuring a closer match to the source in terms of these fundamental visual characteristics. Figure 7 highlights the failure cases encountered in generating fine-grained text. The primary issues include the model's inability to capture fine-grained details such as text engravings, alterations in human poses due to lack of pose consideration, and discrepancies arising from pose-agnostic masking, particularly noticeable in full body coverage scenarios. Table 1 provides a quantitative comparison between different variants of DTC, Diffuse to Choose, and PB-based, a PB variant using DynOv2 and perceptual loss. The table highlights the performance metrics of clip score and FID for each method. PB-based shows a clip score of 85.43 and an FID of 6.65. The Hours Edition variant achieves a clip score of 86.94 and an FID of 6.19. The RCA variant, which uses cross-attention, performs the best with a clip score of 88.01 and an FID of 5.68. This indicates that the cross-attention method is more effective in integrating the hint signal into the main unit decoder. Table 2 presents a quantitative comparison of various Paint by Example (PB) variants on the Vitan No-Face dataset. The results indicate that using all clip patches, PB CLI PAL, outperforms using only the CLS token, PB CLI PCLS, and incorporating DynOv2 and perceptual loss further enhances performance. The best results are achieved by the proposed method, which attains the highest clip score of 90.14 and the lowest FID of 5.39. Table 3 presents the average results from a small-scale human evaluation study, focusing on the similarity of unpainted regions to reference images and the accuracy of their contextual blending. The methods evaluated include PBI-based, DreamPaint, and our approach. The similarity scores are 3.7 for PBI-based, 2.83 for DreamPaint, and 2.9 for our method. For semantic blending, the scores are 3.13 for PBI-based, 2.53 for DreamPaint, and 2.5 for our method. The study involved 20 participants who scored each image on a scale from 1 to 5, with 1 being the best. The paper identifies several limitations in the Diffuse to Choose (DDC) model. Despite efforts to incorporate fine-grained details, the model may still overlook these, particularly in text engravings. Additionally, the model can alter human poses as it does not consider pose, leading to discrepancies, especially for full body coverage. Introducing pose conditioning could help, but the authors prioritized a general-purpose model. In conclusion, the paper introduces the Diffuse to Choose model, designed for the virtual trial application. Key contributions include the use of a secondary unit to infuse fine-grained signals and the refinement of the PB model. Performance comparisons show that DDC outperforms existing diffusion-based Inpainting approaches, particularly in the virtual trial setting, using datasets such as VTON no-face and an in-house dataset. Figure 8 presents a qualitative comparison of the Inpainting methods PB, DreamPaint, and DDC. The visual assessment highlights the effectiveness of each method in generating inpainted regions that resemble the reference image and blend seamlessly within their context. This comparison is supplemented by the results of a human survey, which evaluated the similarity and contextual blending of the inpainted regions on a scale from 1 to 5, with 1 being the best. The survey results indicate that DDC, despite being a zero-shot model, performs comparably to DreamPaint, which requires few-shot fine-tuning with multiple product images. Figure 9 compares the performance of various PB, patch-based encoding, variants against the Diffuse to Choose DDC model. The PB variants include PB CLI-PCLS, PB CLI-POL, PB DI-NO-V2, and PB DI-NO-V2 with perceptual loss. The figure highlights that using all clip patches, PB CLI-POL, outperforms using only the CLS token, PB CLI-PCLS. Additionally, augmenting the image encoder with DI-NO-V2 significantly enhances performance. The inclusion of perceptual loss provides a marginal improvement, particularly in scenarios where the model initially struggled with basic features like color. DDC, however, demonstrates superior performance, especially in preserving fine-grained details of items. Thank you for watching.